Hi, I'm Michael Brand and you're watching How to Lose Money on Analytics, a video tutorial series all about the pitfalls of advanced analytics that we at Otzma Analytics aim to teach people about and help them avoid. This time I want to talk about a specific algorithm that even data scientists are complaining is overused because of the hype that is attached to it. I'm speaking about deep learning, a buzzword that seems to have completely dominated the analytics conversation in recent years. So, what is deep learning, and why, when you're asking for it, you are asking for the wrong thing? The question of what deep learning is a tricky one. As a buzzword, it has been used to mean anything related to artificial intelligence or machine learning or otherwise anything in the analytics space that you might be willing to pay for. The word deep was used in a marketing sense to imply that the computer somehow reasons, thinks, or analyzes, all of which it does nothing of. That's pretty much par for the course for all buzzwords that we'll be discussing in this series. But unlike other technical terms that were hijacked, in the case of deep learning, even the academic meaning of the term has also experienced gradual scope creep. The term was coined in 1986 in relation to hierarchical learning, outside of the scope of neural networks. Later, it was retrospectively pinned to a set of learning algorithms from the early 2000s that were initially applied to something called belief networks and were then migrated into neural networks. Today, the word is used basically exclusively in the context of neural networks, so it's worth taking a moment to explain what those are. Neural networks are agglomerations of what is called neurons or perceptrons that are very simple functions, a threshold function or a logistic regression function that is computed over a set of inputs, and its output is then used by other perceptrons. They are arranged in layers so that every one of the perceptrons uses previous layers as outputs as its inputs. Today, deep learning is pretty much synonymous with the entire field of neural networks. Okay, so that's deep learning. Why is it not what you need? The thing to remember is where deep learning fits into the larger picture of analytics. Deep learning, even if we take by this term to encapsulate all of neural networks, is just one algorithm out of many that a data scientist should know. The algorithms are just a small part of the machine learning theory that the data scientist needs to use. Machine learning theory is just a small part of statistical theory. Statistical theory is just a small part of data science, and even data science itself is just a small part of the overall business process that is analytics. In the Otzma Analytics training workshops, I often go over this diagram, which I call the analytics knowledge stack, as opposed to a technical stack, and explain how each of these layers is rife with pitfalls that need to be well understood and carefully worked around. Specifically, if we consider the red layer, data science, that is a science. It is a research process. Its purpose is to find out things about the world that you don't already know, things that you can hopefully leverage. What is increasingly happening, however, is that data scientists are rushed to skip the scientific process and implement deep learning instead. No science, just an engineering solution. Not only does that completely void the goal of learning, of reaching human interpretable insights, it actually leads in practice to extremely poor solutions. You see, the underlying assumption is that deep learning is the single best algorithm out there. In fact, it's not, and it's not in several different ways. First, the objective of machine learning algorithms is not to learn the examples that are given to them, but rather to be able to extrapolate well to new situations. The models that best extrapolate to new situations are those that best correspond to the actual underlying realities of each situation. The way scientists usually try to ensure this is by use of Occam's razor, always going for the simplest solution that fits. Deep neural networks are among the most complicated models. In a scientific process, they would be among the last to be resorted to, and for good reason. When they generalize in ways that have nothing to do with any underlying realities. These algorithms work well enough when the target environment of interest is well mapped by the training examples. But if you're trying to extrapolate rather than interpolate, neural networks will lead to extremely bad results. A corollary to this is that in order to get good responses from a neural network, you need massive amounts of training data. Most of us don't have this luxury. Moreover, this data must be extraordinarily clean because neural networks are highly non-robust. Even a single bad example can lead to horrible predictions. Consider, for example, a neural network that's meant to create natural-looking faces. While it may oftentimes create faces that look very good, at least at first glance, it's enough to have one training example of a toddler placing a hand in its mouth to create images like these. Neural networks behave this way always, including on your business data. The only difference is that usually you don't have any immediate visual feedback to let you know when such extrapolation backfire incidents occur. And to be frank, for most of us, this idea of massive clean training data is already in the realm of fiction. Businesses can have either massive data or clean data. There's no real way to gather massive data that is at the same time also very clean. In another video, when we'll be discussing big data, we'll see the tools that data scientists use in order to overcome problems of dirty data. But it's mostly done by avoiding fragile algorithms, which neural networks certainly are. Ali Rahimi said this when accepting the NIPS Test of Time Award in 2017.
We apply brittle optimization techniques to lost surfaces we don't understand. And our solution is to add more mystery to an already mysterious technical stack.
In one of his real-world examples, he shows a well-trained system crashing to 99.97% error rate over a completely negligible change in how the rounding of the least significant bit is treated in calculations. These words are echoed by a recently published paper that tried to reproduce 18 top deep learning results. 11 were not reproducible at all, while the remaining 7 were outperformed by much simpler standard methods. The authors end their abstract with the words, "Overall, our work sheds light on a number of potential problems in today's machine learning scholarship, and calls for improved scientific practices in this area," which, to a scientist, is a harsh indictment of the present state of deep learning research. So, their black box algorithm, which make life very hard for people trying to interpret them or gain any insights from them, are too complex to be anyone's front line of defense if using the scientific method, are too fragile and data greedy for practical industry usage, and in fact outside the realm of machine vision and a few other cases, outside of those quite specific cases which don't tend to crop up easily in a business context. Deep learning algorithms have not been shown to outperform standard, often simple, interpretable linear systems. I myself have replaced deep learning algorithms by simple, standard, linear regressions, the simplest of all machine learning methods, and these outperformed the neural networks. And lastly, even in those cases where deep learning methods have been successful, and these examples are well known and well publicized, it's important to look a little closer at what's running under the hood, as is the case in all other successful data science and machine learning implementations that I'm familiar with. Here too, success did not come merely from the application of one algorithm. Successful systems are complex systems, full of moving parts, whose interactions have to be carefully controlled by designers who know exactly what they're doing. This is not to say that you should never use deep learning. It is a powerful tool, and good data scientists know when and how to apply it. What you should never do is use deep learning, or for that matter any other algorithm, as a replacement for the scientific process. Or to use deep learning or any other algorithm without understanding its strong and weak points, and how to control it so as to gain from it maximum value. Without this control, and without this understanding, machine learning systems backfire. And the more powerful an algorithm is, the worse its backfire is. If you want value, look for the simplest system that works, and the one you understand best, both in terms of its behavior and in terms of being able to interpret its outputs and make better business decisions based on them. Everything else would be losing your money on analytics. Have you fallen for this or any other pitfall of advanced analytics? Tell us your story in the comments below. Until next time, happy data modeling, and don't get duped by lies, damn lies, and statistics.